As you will no doubt be aware, our webinars cover topics related to energy, the energy transition, and mobility. For over 3 years now, we have been welcoming graduates specializing in these fields to give a talk. About the organization of tonight, as usual, there will be 2 Q&A sessions, so do not hesitate to write your questions and we will convey them to our guests. The Q&A sessions will be facilitated by Sabine Assizad, and Sabine is a student in the Processes and Polymers program, and he will be helped by Denis Bossan, and Denis is a lecturer at the school. So we are going to be discussing hydrogen this evening, and it is also one of the topics covered at the school now. I would like to take the opportunity to tell you that to start 2024, we deliver 2 MOOCs dedicated to hydrogen. First one is hydrogen for mobility, and the second one, hydrogen production. And they are open to all and free. You've got the QR code on the screen in order to register. Then, second part of the screen. Our range of degrees is expanding to an 18th program. We launch an advanced master degree, Master Spécialisé, on hydrogen project and engineering. It is open to students with an engineering or master degree or a BSc with 3 years of professional experience in the energy sector, and also open to professionals. It will start in September, and the application period is open via IFP School website, and also all information via this QR code on the screen. But for now, we are very pleased to welcome Bruno Lestrade and Alice Rodrigues. So let me introduce them. Bruno Lestrade is Business Developer CCUS and Power-to-Methane at GRTgaz. A graduate of Chimie Paris-Tech, he holds a degree in refining, engineering, and gas from IFP School, class of 2003. He began his career in oil refining before switching to energy management, where he worked across several industrial sectors, such as metallurgy, chemicals, and power generation, on both technical and economic levels. Today, at GRTgaz, he supports natural gas customers in the energy transition towards renewable energies and low-carbon gases in particular. Since 2023, Bruno is a lecturer for IFP School Energy and Processes program. He is also a member of the Conseil supérieur de l'énergie. Concerning Alice, Alice Rodrigues is a graduate of Agro-Paris-Tech, class of 2004. After 2 logistics positions in the food industry, Européenne d'embouteillage, Kerry Produits Jaeger, she joined GRTgaz in 2009. She worked for 5 years as an IT project manager on GRTgaz Transaction Commercial IS, then for 5 years as a routing account manager. Since 2019, she has been carrying out dimensioning studies on future all hydrogen networks. Tonight, Bruno and Alice will present the GRTgaz RTE study on the needs and joint planning of hydrogen and electricity infrastructure. So please, Bruno, Alice, I give you the floor. Thank you.
Let's talk about hydrogen and also electricity, because both are very linked, and that's the whole topic of this study that we have conducted together with RTE. Before going into that presentation, I just need maybe to introduce to you the 2 companies, RTE and GRTgaz. We are 2 what we call transport system operator, TSO in English, and we are in charge of operating for RTE. They are operating the electricity network in France, the major one, And for GRTgaz, we are one of the two TSO operating the natural gas network in France. We are in charge of building and managing those two networks. And that makes a lot of sense for us to make this study that started in 2022, to start looking at how we could implement an hydrogen network that is really complementary with the electricity network on one side and the natural gas network on the other side. And that was the whole purpose of that study, to try to look how to build such a hydrogen network. If you can maybe switch back to the presentation. I don't know who is presenting.
Alice, are you there?
Okay, so I'm gonna present.
Please come back.
No worry.
Alice?
Sorry, I think I was disconnected. Let me.
Can you present again?
Yes, sorry.
No problem. So the idea was to bring together the best expert that we have at GRTgaz on one side and at RTE on the other side, and try to really bring on paper all the hypotheses you need to take into account when you start thinking on how to build an hydrogen network. As you may or may not know, hydrogen is mostly considered to be in the future produced by electricity conversion through electrolyzer, and this will require lots of power. So it will have an impact on the power system infrastructure. And you have to decide, if you start to think on how to implement the infrastructure in the future, you have to decide whether you're going to put the electrolyzer next to the consumption site, and therefore you will have to bring electricity to the consumption site, or you have to think, if you put the electrolyzer to the production site, the electricity production site, and then, of course, transport that hydrogen to the consumer. And that was the start of that thinking in how do we do to decide what is the best option. So we bring together the best estimate that we have on how will be the hydrogen market in the future, how does it cost to build hydrogen infrastructure. And because we wanted to make that study the most robust, we decided to make a consultation. We have published end of 2022 the main hypotheses that we were going to take to conduct that study. And we sent that to our main stakeholders, and they had the opportunity to comment, to bring back different hypotheses, especially in terms of hydrogen storage. So we discussed a lot with Storengy and Terega, two main operators of storage. Terega is also a TSO of natural gas in the southwest of France, so they has a lot of experience on how as well to build network and optimizing them. So the analysis was to take into account all the interdependence that you can expect to have between a hydrogen network, electricity network, but also methane network, because you will see later on that building a hydrogen network will have an impact on the methane network. You can move to the next slide, Alice. The three main objectives. Well, the first non-objective was not to try to determine what is the best energy mix for the French electricity system. That was not the purpose of that study. RTE is looking at that. They made a lot of publication on that as perspective. GRTgaz is also doing that for natural gas, biogas, and hydrogen. That was not the aim of that study. The study there was just to try to see how do you build an infrastructure. So the first point was to try to see if you foresee a low final hydrogen market by 2030, by 2050, does that still make sense to build hydrogen infrastructure for such a low final hydrogen? That was the first thing we wanted to prove, or to maybe not prove. The second point was, of course, to try to draw the main cost and benefit that are associated with a flexible hydrogen system, and I will come back to that later on, the definition of what we consider to be a flexible hydrogen system. And then, of course, when you do such a study, you try to determine the sensitivity on your different hypotheses to see if you change one hypothesis, the result is changing or not. So that was the three main points. And last but not least, because we are TSO and not a regional or local system operator, we focused on the big picture. So we were looking at regional equilibrium, national equilibrium. We did not went into the detail of the main cities or the suburbs or stuff like that. We really, the big pictures to start with. And the next slide, please. Those are the 8 most important hypotheses that we took, among which we decided to keep 4 fixed and 4 that you can fluctuate. With, concerning the electricity consumption, we are based on the Futur Énergétique report from RTE. That's their perspective on how the electricity consumption will look like in 2050. And we took the scenario N2, for those of you who know those type of study from RTE. We considered that hydrogen was produced only in France for the part that is consumed in France. So the idea is that we have an autonomy of hydrogen, but we have considered that there could be transit through France of hydrogen produced elsewhere to consumer elsewhere. So that is the third that's the third point here, that we have made fluctuate in our study from a big transit to no transit. We also took the mix for the electricity generation that RTE has put in his report. We consider that hydrogen production was produced only by electrolysis. It is the main production possibility today. So we took that hypothesis. We could discuss that. And the last 3 that we consider that could fluctuate in our study was the consumption of hydrogen is the first one. We took 2 hypotheses, a low one and a high one. And when we started that study in 2022, the high Y was very high, but nowadays in 2024, the high one is maybe not that high. So at the end, we are quite happy with the 2 hypotheses there, the 35 terawatt and the 120 terawatt of hydrogen. Then we also took as a possible fluctuation is the position of the electrolyzer. That's what I mentioned earlier, is do we put the electrolyzer at the consumption site or at the production site? And then the flexibility of the hydrogen, do we consider that electrolyzer has to fulfill the demand all the time, whatever the demand is and the production is capable of, or the other way around? Do they produce only when they have low carbon electricity, whatever the demand is? And Alice?
Yes, thank you, Bruno. I will go into further detail around this hypothesis because it's the most trickiest of all of them, and it's also the one which has started the financial estimation. So our reference scenario is a scenario where there is flexibility and there is an hydrogen infrastructure, which means that the upper part, which means that the electrolyzer can adapt their operation regarding on the availability of renewable electricity. On the other side, the complete opposite is a fictive scenario where, first of all, electrolyzers are not flexible at all, which means that they are on operation all year long, no matter the availability of renewable electricity. And that means also that in this case, there is no need for storage and no need for any hydrogen infrastructure. In this case, the flexibility that the power grid needs cannot be fulfilled by a hydrogen system, so it must be met by another means. So this part is more a result from the Futur Énergétique from RTE, but it's a very big point. The power grid needs flexibility, and that must come from molecule, either hydrogen or methane, but it's mandatory to have molecule to store energy. Here, this part comes directly from Futur Énergétique. It explains more into details why there is a need for flexibility. As it comes from another study, I will not explain furthermore, but I want to explain why it's more efficient to use hydrogen rather than methane to give this flexibility to the power grid. So here is a comparison of those two big scenarios. On the left side, we have the case of no hydrogen grid, no hydrogen infrastructure, and on the right side, it's the reference scenario. In both cases, the final consumption of hydrogen is the same, and it is flat. It's flat because it comes only from industrial. In our hypothesis is that there will be no public distribution. It's only industrial consumption, and so we can take a good hypothesis that the consumption will be the same all year long. Sorry. And so, in the case where the electrolyzers are not flexible at all, it means that they are functioning all year long as well, no matter the availability of renewable electricity, which means that when there is a lot of renewable electricity available, there is a lot that is not valued because there is no electrolyzers for it. And on the contrary, when there is when we are on the peak days where no renewable electricity is available, then the grid, the power grid needs to call for CCGTs to produce electricity. But in the same time, the electrolyzers are still working. So we are in a sort of shadow situation where we are using methane to produce power, to produce hydrogen, with all the efficiency that we know when we multiply such combinations. And of course, we need the CCGTs, so we need a peak capacity to answer to those situations. On the other case, when the electrolyzers are flexible, they can adapt their functionment, and so they can produce hydrogen when there is renewable electricity, and they can stop when there is not enough renewable electricity. In this case, of course, it's quite obvious the efficiency is better, but also, well, then we have to have more electrolyzer installed, and of course, we need a nitrogen system. But in this case, there are still economies that we can begin to feel. We have estimated that the hydrogen infrastructure brings about 15 terawatts of energy savings, and also about 5 terawatts of peak capacity not needed. So that was the CCGTs.
One question about the production of the hydrogen through the electricity versus the production of the hydrogen through the steam methane reformer. What are the advantages and disadvantages?
Well, if we speak of today, 2024, electrolyzers are only a beginning technology, so we don't have yet a lot of history and recs about it, and therefore it costs more than steam methane reforming. But at the horizon of the study in 2050, then we hope for the climate, we hope that there will be no steam methane reforming anymore. Well, that's the tendency that we see in all publication about the subject. That's what's in the Future Energetic. So that's the hypothesis that we have taken into account. Bruno, you're more expert than me on the technologies.
It's also that if we wanted to compare the low carbon hydrogen production, you have to compare low electricity electrolyzer towards steam methane reforming combined with CCUS. If you do so, then you don't have, if you consider only the SMR, you don't have an impact on the electricity network. However, you need a CO2 network. So that would have been a complete different study with hydrogen network, CO2 network, and methane network. Because if you estimate that your hydrogen in the future will be produced by methane, then you need also, you will have also an impact on the methane network. And that would have been a study that we could conduct without RTE, because the idea here was really to study what is, as for today, is the main hypothesis of what will be the low carbon hydrogen in the future. At least that's the route that France is taking today with electricity and not CCUS on SMR. Or you could also use biomethane and SMR. So that's also a more expensive technology as for today.
Thank you very much. There is another question. Is there any similar study in the Europe related to your study?
No.
Or in other countries?
It's, well, Alice, maybe.
Yeah, we considered other countries, not because we find ourselves experts to say what's the optimum on their countries, but more that because neither power, neither methane, neither hydrogen can work in total autonomy. On a net balance, yearly balance, it is the country France is autonomous, but on a real-time basis, on a hourly basis, there are times of the year when we need to import or to export either electricity or hydrogen, not for methane in this at this horizon. That's why we have considered the other countries. And also, we had one topic on which we have taken different options, which is the transit. And so to modelize the transit, it has no sense to make it without considering our neighbors. So we have modelized the other countries, but on a simplified way. They were modelized as one point, one contractual point, and not, we haven't tried to represent the reality, the physical network.
And if the question was about, does the same study has been conducted in other countries in Europe, then the answer is no. That's the first time that two TSO, one from electricity and one from the natural gas world, are working together to build, because what Alice is not saying is that we needed to build together a model that fits electricity and natural gas and hydrogen. And that specific work has not been done in other countries for a simple reason, is that France is quite unique. We have few TSO compared to the size of our country. In other European countries, you have many TSOs, and I think it makes the world a lot more complicated for them to, well, to work all together on the same model with the same hypothesis. Do you have another question, Sabine, maybe?
Yes, I have a question. How is the electrolysis process taking into account the exploitation of the valuable metals, for example, lithium? And how the procedure is done, especially in France, the recyclability of the valuable metals?
So we haven't taken the primary, the resources into account in this study. We know that that would need that raises a lot of questions, but that was not the aim of the study.
It was a very interesting study to conduct, and especially to look at the results. Especially when, again, the first objective was to look at the situation with a low hydrogen market. And if we look at the low hydrogen market, and if you look at the flexible hydrogen system in the way that Alice just described to you, we find that it's very important to get access to storage. You can't have a flexible system without large hydrogen storage volumes. This is something you have in mind even beforehand starting the study, but what we wanted to assess is what was the capacity needed to match that flexibility. And we were quite surprised to see that you need quite a large amount of hydrogen storage capacity, even for a low hydrogen market. So the results were that you needed 10 terawatts of storage for 35 terawatt per year of consumption. We don't have that on the natural gas network world. That was a very specific result of that study. The good point is that when we discuss with the storing operators, we find out that in France, it's reasonable to think that we could have 10 terawatt of capacity. And it's also reasonable to think that we could take that capacity out of the methane system and putting back to the hydrogen system. Because when we're talking about gas storage, you have two technology. One is aquifer, so let's say water, salty water underground, and the other one is salt caverns. For hydrogen, so for the natural gas world, you can use both, but for hydrogen, it is preferred to use salt cavern. So if you want to bring 10 terawatts of capacity, you need to convert the actual natural gas salt cavern into hydrogen salt cavern. So on one hand, you need to check if that is enough for the hydrogen world, but you also need to check if the methane world can live with such reduced storage capacity. And the answer is yes. So it is the conclusion was it is possible. It has a cost, and we will discuss cost later on, but it is possible. The second result was that if you go to a high hydrogen market, about 120 terawatt, you need to increase your storage capacity, but not in the same extent. So you need a lot more, but not such a lot more. So it's 25 terawatt approximately. But it is a challenge because we don't have that capacity yet. So we will need to develop new capacity, maybe even consider hydrogen in aquifer, which is today not ready yet technology. And of course, the third option would be to connect the French system to other countries, especially in the east of Europe. They have, and in the north, you have countries with a larger salt cavern deposit that you could use and convert to hydrogen storage. Next slide, talking about money. If you can. So, the main result was that if you want to build a flexible hydrogen system, you will have some benefits on the electricity. That's what Alice explained earlier, and that is quite logical. And if you put numbers to that, we find out that you can make savings of around 2.5 billion euro per year, because you will have less power generation capacity needed, you will increase your energy efficiency, you will have less electricity infrastructure to build. So that makes sense. And with the hypothesis that we took, the overall saving is 2.5. But on the other hand, you need to build an hydrogen system, both storage, electrolyzer, and hydrogen infrastructure. And that is a cost of $1 billion, sorry. And in overall, you have a net benefit of 1.5 billion euro per year. And that is only with the low demand scenario of 35 terawatt in 2050. And
if we put that into a graphical map, we can see what are the biggest impacts and what are less impacts. So again, the net benefit is a 1.5 billion euro per year. Those are annualized costs. So that's why this study is really interesting, because it proves that the hydrogen infrastructure and the storage really are really a big benefit for the energetic transition for France, and we can probably think the same for other countries. As we said, so on the left of this graph is the case without hydrogen flexibility, so electrolyzer fully flat. Here are the economy on the power grid. So we said less CCGTs, less reinforcement. Here are the costs of the hydrogen system. Of course, we have to build to put new pipes and so on, to convert storages, to put more electrolyzers. But all the same, altogether, the economy is really consequent. Of course, if we think about the global cost of energetic transition, we may think it's not that much, but still it is really a proof. And one more word about the storage. We used to hear a lot that small local storages at near the consumption sites might be enough. When we think about the 10 terawatts needed, it's not small local storages. We really have a wide storage need. So that completes the picture of this hydrogen network. So now we have seen the cost, but what does it look like, this hydrogen network? So there is a first map. So that's the map. Again, it's the reference scenario. The different color of the pipes here indicate if they are new or converted pipes from methane. And what we can see already is that it is a quite wide network. It's not only a small part of France, it really goes almost everywhere. And why that? Because again, we need to connect to the storages. We cannot work only on local artificial storages. We need to connect to the big storages. And the storages, which are salt quality, are mainly on the Rhone Valley. Not only, but the biggest part is clearly here. And so we need to connect the consumption areas, which are mainly the industrial basins, the production areas, which are not always the same, but still quite all over France, everywhere. And so the storages. That's why we have such a wide network. There was a question, one of the objectives was to see if there is an impact on where we put the electrolyzer, if they're more near the consumption site or near the renewable electricity production sites. And in fact, it doesn't matter that much. There, we will see the economics about that, but in fact, again, we always need to connect the storages. And well, no matter what the electrolyzer, we need to connect the consumption and the storages, which means that the final map is always more or less the same. So when we have shown those numbers and those maps around us and to the public authorities, they have been a little bit impressed because when you see all the network that needs to be built and you can see all at once, it may seem a lot. And so they asked, is there a roadmap that we could propose? And so we have tried to imagine, to explain a little bit what would be the different steps of development of such an infrastructure. And well, first of all, again, always the same thing. First thing is to connect the storages to the small, we speak of hubs, the small little ecosystems and the storages. That's what we are already doing at GRTgaz. We are working, for example, on the Faust-Manosque area. Storengy is also working on his storage of Etri. They also have a project called Storgreen, and well, a little bit like a little more like that. So that will be the first part. Connect the storages. Then a second priority would be to connect the biggest industrial basins. The biggest one that needs to decarbon his economy is around Dunkirk, but not only. And so that creates a sort of north to south corridor to connect up to Dunkirk area, all the Grand Est region, and down to the south at Fos, where the future pipeline Barmar will arrive. And in a third place, then we will have the northwest of the France. Why is it at a third place? Because here the potential of electrolyzers does represent only 11% of the national consumption, which means that
Alice, can you hear us? Hello?
I think she was disconnected.
She's having issues with her bandwidth.
I'm gonna.
Please bear with us while we wait for her to reconnect. Thank you for understanding.
consumption, and this one was
Alice, can
near
you
the
hear us?
production
Alice?
sites. Yes.
Alice, sorry, you were disconnected, so we lost you. Could you rephrase your previous paragraph?
Of
Yeah,
course.
we lost the end of the former slide.
Sorry.
Come to that one.
Sorry about that. So I was saying that the little bit less priority region was the north to west zone, because well, it doesn't impact that much the flexibility of the power grid, and also it's further away from the storages, and there is less possibility to convert methane pipes. So that comes in the that's why it comes in the third place. Now I wanted to talk a little bit about the place of the electrolyzers. The comparison of the economics, if we put them near the consumption or near the production sites. So the first part of the slide, that's always the same. And so I'm not comparing this one and the last one. And we can see, again, there are some economy and some extra costs. But in the end, there is a little economy if we put electrolyzers near the electricity production. In other terms, that would be, it costs a little bit less to transmit hydrogen rather than to transmit electricity. Well, to be completely honest, the economy is quite negligible regarding all the other costs that we have already mentioned. But still, the study can put a stop to the general idea that we only have to put electrolyzer near the consumption. Well, it's not that true. It may be true in some territorial places and not in some others. And so in the end, the optimum has to be searched on a case-by-case basis. But it's still a very good result, because for the moment we did not have any numbers to argue, and now we have now we know what to think. And now I will conclude the study to say that well, the main benefit brought by an H2 system is that we can connect hydrogen basins and storage facilities, and that has a very big value both for hydrogen network, of course, but also for power grid, and that's a really important point, an important result of the study, because it allows the electrolyzers to modulate their functioning, and so to modulate the power consumption, and that brings a very important flexibility to the electric system. On the second hand, but not as important, the location of electrolyzer is also brings also some benefits, because it allows to make less reinforcement on the power grid on a more limited scale, of course.
Question and answering session for the second part. So first question, so what is the range for the storage capacity which has been taken into account for the costs?
So that was the consultation that has been confirmed by both Chargée and GRTgaz. And do I have numbers somewhere? I can send you the link to have a look at the public consultation where there are the numbers inside, because
I'm not sure that they gave the detailed size of each storage. You have a map. On the map, the size of the triangle is proportional to the estimated storage capacity. So, but you have small storage of 1 terawatt in southwest and in the east region of France. You have a bigger one of 2 terawatt along the Rhône, and the biggest one are Fos, Manosque, and the north, close to Lyon, and that's only 4 terawatts. That's what you see here, and you have the size. But this is, of course, very approximate data, because so far it's still an ongoing process to fully determine the size and the economical size of the storage.
Okay, thank you very much. Another question: does the introduction of the hydrogen storage reduces the electricity imports into the France?
At this horizon, France is autonomous on a yearly basis, either in electricity and hydrogen, of course, and in methane. So yes, it will reduce. Well, there will be some imports and some exports, but on a global net value around the year, there will be no. France is autonomous.
Okay, thank you. Next question. Are there any storage projects along the River Seine and the Loire Valley?
That's what I have answered in the chat. We don't have any project that we know of.
Okay, thank you.
But looking at the new hydrogen capacity storage is a thing. So you can be assured that the company that are expert in that domain are looking at, in the whole Europe actually, on where they could store hydrogen. You have exactly the same on the CO2 storage studies that all the operators are launching nowadays. So everybody is looking under the ground what you can store or what you can produce, such as lithium. So that's a very interesting topic for our colleagues of geology.
Okay, thank you very much. Next question: what are the next steps and agenda after your study?
Well, first of all, as we've seen, we need to search for optimums on a territorial case-to-case basis, and so we are working on those paths. So we will not study the whole France because that would be infinite. But in the local ecosystem that we can already see here, we are already trying to see if we can find optimums on the localization of electrolyzers. And well, as in all projective studies, hypotheses and knowledge improve all over the time, and so there will certainly be an update in the future because we will have new hypotheses to take into account.
Okay, thank you very much. In the presentation, there were the figures 35 and 120 terawatt per year. How many percentage of the total electricity does it represent?
This is a significant part because the electricity consumption in the N2 scenario is up to 650 terawatt.
Yes.
So you need to take into account the yield of the electrolyzer, but you have all those data is in the report. So that's why I sent the link in the conversation in the Q&A. You will find more information on all the type of hypotheses that we took. Actually, this is coming from RTE and their scenario that they are looking at on what will be the evolution of the electricity consumption and production in France by 2050.
Thank you. Next question.
Again, just the aim of that study was not to look and criticize positively or negatively those scenarios. The question was, if we assume that those scenarios are right in terms of electric consumption and hydrogen needs, what is the best option to bring that hydrogen to the consumer? That was really the focus of that study.
And another question by the Nicholas Goldet. What is the cost of the hydrogen production in terms of the energy consumption as well as the overall economics and money?
Very interesting question, but I don't think that we have the answer because we are not looking at we are not a producer, neither is RTE. So the cost of hydrogen is something very speculative at the time.
But still in the study, well, that's not the part I'm expert on, but I remember we have taken into account again the availability of renewable electricity on the cost of hydrogen at the moment. So there were some well, the cost of hydrogen was not considered constant all through the timeline that we have performed simulations on. but I cannot say more because that's really not my part.
The only thing we have been looking at is the cost of hydrogen infrastructure. This work has been conducted together with the other TSO in Europe, and we were looking at how much does it cost to bring a European hydrogen network, what we call a hydrogen backbone, that is the size necessary for what the market is expecting in the future. And we've conducted that study to make sure that the cost that we foresee is much lower than the expected cost of the hydrogen molecule. The expected cost of the hydrogen molecule depends on who you are listening to. Some people expect the hydrogen to be as low as 1.5 euro per kilo of hydrogen, and some see that price up to 10 euros or 15 euros per kilo. It really depends on how much you're going to consume, what type of electricity you're going to buy, and so on and so on. So, but the range is some euros per kilo. And what we have been looking at is that together with all the TSO, and that's the link that I put in the chat as well, the European hydrogen backbone, we know that we are below the euro. The infrastructure cost is below the euro per kilo, compared to more than, well, several euros per kilo of production cost. Production and purification, because I saw that there was a question about purification.
Yes, thank you. Next question is about the pipeline, whether the pipeline includes the monitoring of the potential leakage or not.
Yes, leakage is of course a very important topic on the safety theme in general. Well, we already are very interested. We monitor very precisely already the leaks for methane network, and so we plan to monitor it as well on hydrogen network. According to the state of the art today, the monitoring will be even more detailed because, of course, any leaks of hydrogen are a very big problem. Yes, Bruno.
But there is something very important that we need to address here. People in the public are talking about leaks. For a transport system, there is no leak. We don't have holes in the pipes that are leaking natural gas or in the future hydrogen. We have losses because of maintenance operation in which we require to release gases to the atmosphere. They are called leaks, but this is no uncontrolled leaks. We don't have uncontrolled leaks since years on the natural gas network. I'm talking about transport network. I'm not talking about distribution network because they are using different technologies and at a much larger scale. But on the big pipes going through the ground in France and all Europe, there is no such as leak. To be very precise on the term. And we don't expect to have leak on hydrogen because that would be just too dangerous to have. But we will have losses.
Yes, thank you very much. Another question is about whether it is possible to also transport the natural gas through the hydrogen pipeline or not.
Yes, that's exactly what we are looking at in the European hydrogen backbone is to, but that was not the aim of that study. The other study was to determine how much of our infrastructure from natural gas we can repurpose to transport hydrogen. And that study is another study, actually. Maybe, Alice, you know more as well.
But I think the question was to reconverse from hydrogen to methane. Is that correct?
No, to methane to hydrogen.
No, it's pipe.
Okay, so yes, so there are lots of studies going on, especially for example, the European hydrogen backbone. And so yes, we are confident that it will be possible to convert a pipe from methane to hydrogen. There are some risks to address. Yes, thank you. But it's ongoing, and we are confident.
And the first project that is going to be that is public and that is going to start by 2027, if I'm not mistaken, the Mosaic project will be an hybrid project with part of the pipes that are repurposing natural gas pipe to hydrogen, and part of the pipes that will be new pipes.
Okay, thank you very much. I think it was the last question.
Thank you.
That brings us to the end of our question and answering session. Thank you for your time and attention. At the end, I will give the floor to Sabine.
Thank you very much, Bruno. And Alice, for your talk. It was a really enlightening and rich talk. Thank you all for your participation and question. And we will be pleased to see you in March for a new webinar in a new format. And we'll send you all the information. And just to end this webinar, you can help us raise awareness of IFP School position as a key player in hydrogen training by sharing the information on your screen about our MOOCs and Master Spécialisé. So thanks in advance for your help. Enjoy your evening and see you soon.